Just as we worked with the electric force in 2 dimensions, we're now going to do the same for the electric field. We can find the electric field due to 3 or more charges that do not fall in a line. The electric field, and again this is a review, is represented by vectors at every point in space. It can be calculated at any specific point in space. There actually doesn't have to be anything there, but the electric field is there. We're going to start by establishing perpendicular axes that are symmetric to whatever problem we're working on. Determine the field at point C due to charges A and B. A is plus Q, B is plus Q. Note, there's absolutely nothing at point C. We just want to find the electric field there. So let's start with the appropriate coordinate system, and we will draw the electric field vectors at point C due to the 2 charges. As we did with a similar problem for electric force, we have a Cartesian coordinate system here, and we center it on point C. The electric field at point C from charge A is on a line connecting the 2 points, and since this is a positive charge, the electric field points away. So here is the electric field due to point A. The charge at point B does the same thing, but that line's pointing this way, so here's the electric field due to charge Q at point B. This picture indicates that this angle here is 60 degrees. How did we do that? And also, this angle is 60 degrees. Since this triangle that we made from the 2 charges and point C where we want to find the electric field is an equilateral triangle, you can see how all the distances are the same, this angle here has to be 60 degrees. Now the corresponding angles theorem, and we're going to use that, we'll extend this line here so that this line is parallel to the x-axis. This angle is a corresponding angle to this angle. So the theorem indicates that this angle has to equal here, so this is a 60-degree angle. The next step is to use trigonometry. We will be resolving these 2 electric field vectors along the x and the y-axis. So we'll have EAY, EAX, then EBX, and EBY. The next slide will show you what that looks like from a vector point of view. We add vectors by adding the tip of one to the tail of another. So here is the tip of EB. We take EA, slide it over here. See how we're just translating that way. And the tail of EA is now on the tip of EB. We get a point here, we connect that to the origin, and that's going to be our total electric field. We also could have added EB to EA, and that's what this is, and fortunately it gets to the same place. So that's the vector way to do it. Now let's look at the trig way and the algebra way. Calculate the value of EB and EA. EA actually turns out to equal EB, so we're going to get rid of the subscripts and just call it E. Why is that? Well, here's the equation. It's KQ over R squared. Both charges are exactly the same, and both are the same distance from this empty point in space. So we have a value for E due to each charge. Now let's find out what the component of the total field is in the x direction. Well, that's EAX plus EBX. And to find this value here from a triangle, it's the hypotenuse, which is E, times the cosine of 60. The field due to charge A is to the right, so it's positive. The field due to charge B is negative, and look, they cancel out. We get a 0 electric field in the x direction. For the y direction, we're now using the sine function, and you can see both of them are going up. They're both positive. So I'm going to get the sum of the electric fields in the y direction, once I plug in what the sine of 60 is the square root of 3 times E. Now to be terribly formal, although we don't really need it in this case, the total E is going to be the Pythagorean sum. It's the square root of EX squared plus EY squared. But there is no EX, it's 0. So the total electric field is actually the total electric field in the y direction. We now substitute in for E, which is kq over r squared, and we get the total electric field is radical 3 kq over r squared. We also have to give a direction because it's a vector. The previous slide we showed how it points straight up. So our total answer is, here's your magnitude, and the direction is straight up on this piece of paper.